Welcome to our Sigma tutorial on protocol security and privacy for database systems. This tutorial was prepared by 6 researchers who have been working with privacy, security, and database systems for years. The team includes she/her myself from the University of Waterloo, Jenny Regis, and Sean Wang from Northwestern University, Johannes Bader, Chenhong Wang, and Ashwin Macharajahala from Duke University. The success of the database systems have been greatly attributed to the researchers and practitioners in this database community. Today we find database systems everywhere, from personal data clouding to business management in corporations. There are many reasons for the popularity and importance of database systems in managing our data. Its logical data model and declarative queries allow a graceful separations between the logical layer and the physical layer of the systems. In particular, the users and administrator of the system do not have to be database system experts. The system can take care of challenges in multi-user concurrent access, data recovery, and scalability issues. But there is one big problem that modern database systems are not fully ready: security and privacy. As an enormous amount of sensitive person data has been collected and kept in cloud or accessed by untrusted third parties, such as location data, smart home devices, we see many security and privacy problems in the news, and no mention of companies who pay millions of dollars of penalty for their improper collection or sharing of sensitive data. There is a desperate need for an end-to-end system solution for non-experts that can manage the sensitive data without breaking security and privacy. Do we have a way out? A quick answer is yes, we have a way. We have a hawk. We have a lot of power, strength, and 7 PhDs. This approach seems possible. In particular, the security and privacy community has developed a rich set of techniques in the past. Though they do not address the end-to-end workflow of a query execution, we can hire multiple PhD level specialists to deploy the techniques for a particular setting. This is the approach taken by some big data companies. Unfortunately, not everyone can afford that. In addition, these solutions are usually hard-coded, and hence they cannot be easily transferred to other settings. How about general database system solutions for security and privacy? There has been some, but limited work on building end-to-end systems with security and privacy guarantees from the database community. But each has its own focus of assurance, either in data privacy or secure query evaluation or query verification. A naive integration of these assurance or techniques may even lead to new privacy attacks. In addition, composing this assurance is a non-monotonic cost model for query optimization. It has a much larger optimization space than traditional database systems. How do we get the best deal is non-trivial. It is possible that we pay a huge performance cost but end up with no end-to-end security and privacy guarantees. Last but not least, solutions developed by experts are not necessarily perfect. For example, many cryptographic techniques developed in the past for secure communications has been broken today. We don't want the same thing to happen to our database systems. Therefore, we must take a principled and systematic approach for developing the next generation of database systems. This system will need to treat security and privacy as first-class citizens in their design. This paradigm shift impacts virtually every aspect of database systems, such as how we can access data to how we prepare query results for the user. Hence, it impacts on many core database challenges such as query optimization, storage management, and database operator algorithms. Hence, in this tutorial, we first focus on the principles for defining and designing security and privacy solutions. Second, the primitives that support these definitions. And third, challenges and approaches for system integration and optimization. We have 3 modules that target each of these focuses. The first module covers defining security and privacy requirements for database systems. This focuses on the background, problem setting, and definition. In particular, we will present common architectures in this emerging landscape, and will identify when and where each will need to incorporate security and privacy techniques. Note that we won't be able to cover all the techniques in detail. Hence, in the second module, we'll focus on a few of these requirements and techniques that include secure multi-party computation, trusted execution environments, and differential privacy, to demonstrate these principles that we brought up in Module 1. We also break Module 2 into 2 parts, 2A and 2B, so that we can take questions and a break in between. Module 1 and Module 2 are intended to give general database researchers an overview of the security and privacy landscape in database systems. The second module also provides essential toolboxes for researchers to integrate security and privacy into their own systems. The third module on system integration and optimization provides case studies. These studies show the opportunities and challenges in building practical trustworthy database systems. This module also provides an overview of cutting-edge research that may be of interest even to experts. Time-wise, we plan to complete the first module and Module 2A roughly by 10:50. Then we will take a break and restart our session by 11. We plan to complete the rest of the module by 12:20. We will take questions in between every module that also include the break and the end of Module 3. Now let's come to our first module, defining security and privacy requirements for database systems, or in short form, SMP requirements. You may ask why we want to start with this topic instead of any classic algorithms or the state of arts. This is because defining SMP is a fundamental question and a key principle for modern cryptography. Unlike heuristic approaches that evaluate the solutions based on their perceived complexity or cleverness, this modern and systematic approach aims to provide rigorous proof that a given solution is secure. In order for us to articulate such a proof, we first need a formal definition that pins down exactly what security means and why such definitions are useful or important. Second, we also need all the assumptions made by the construction to be stated precisely and explicitly. This is because most proofs rely on currently unproven assumptions about the algorithmic hardness of certain math problems, and are related to the power of adversaries or attackers that may vary among settings. Hence, it is important to have precise assumptions stated for the understanding, validation, and comparisons of different SMP solutions. In particular, many SMP solutions are not run in isolation. They're part of their complex systems. Hence, we like to ensure they can be composed easily without breaking each other's guarantee. Last, it is desired that the methods are not hidden from the adversary, or the guarantees should not be achieved via obscurity. Given the formal definitions and precise assumptions, a proof of SMP solution can give an ironclad guarantee that no attacker will succeed. Note that this approach does not end this age-old battle between attacker and defender, but it does provide a framework that helps shape the odds in the defender's favor. Therefore, we would like to take this probable SMP approach when we design and build practical systems for privacy and security. The definitions of SMP greatly depend on the architectures and settings. We need to answer the following questions. Who are the attackers or the point of failure? Are they the clients or the servers of the database systems, or both? Or what to protect, the input data, the query evaluation, or the query itself? Is it about their contents or their integrity? If we want to achieve these security and privacy goals, where shall we integrate them into, and at which level? In particular, do we offer protection at cell level of the table, or the record level, or the table itself? Do we design primitives at operational level, or query level, or transaction level? These choices affect the final guarantees and also performance optimizations. In this tutorial, we will examine 3 reference architectures. First, the client-server setup, where the data sits on a server owned by a trusted data broker, but the client is untrusted, where we put the devil picture beside it. The second reference architecture considers the case where the sensitive data is federated and there's no trusted central server or data broker. Lastly, the cloud service provider setting. In this setting, both data owner and the client are the same party, but they outsource the data to untrusted cloud for storage and computation. These 3 reference architectures are not meant to be exhaustive, but they provide a canvas for us to illustrate the desired SMP definition and ways to achieve them. Among these reference architectures, the untrusted parties are considered as attackers or corrupted parties. In this tutorial, we focus on the static model. That means the set of parties controlled by the adversary is fixed before the protocol begins. Honest parties remain honest throughout, and corrupted parties also remain corrupted. Despite they are all untrusted, there are different levels of trust assumptions for allowed adversarial behavior. We'll cover 2 types of common trust assumptions about the attacker's behavior. The first type is the malicious adversaries. The untrusted or corrupted parties can arbitrarily deviate from the protocol specification according to their instructions. In this way, they can either gain unauthorized access or make changes to private information. Such adversaries are also called active attackers. In general, providing security in presence of malicious attackers is preferred. It ensures that no adversarial attack can succeed, but it usually incurs high performance costs and implementation complexity. Hence, a weaker assumptions made by adversary is usually considered as well. It is semi-honest adversary model, when the corrupted parties correctly follow the protocol specification. However, the adversary obtains internal states of all corrupted parties, such as the transcript of the message, and they can use them to learn information that should remain private. Semi-honest adversaries are also called honest but curious, and a passive adversary. This is a rather weak adversary model, but a protocol with this level of security does guarantee that there's no unintended data leakage. Protocols with this assumption are more efficient as well. We'll now examine the set of SMP notions and techniques with this semi-honest party assumption, with all these 3 reference architectures. First, we're going to look at client-server setup. In this setup, the client would like to learn something from the data owned by the data owner. For instance, data analysts who are interested in learning population statistics will make queries on their data. It is commonly assumed that the server is a trusted data broker acting on behalf of the data owner. This data broker has the true and plain text data stored and processed on the central server according to a valid computation. In this scenario, the client, such as a data analyst, who will send queries to the server. The server will obtain the query answer and return a private query answer to the client. In this case, the client is the attacker, who like to infer sensitive information about individuals from the released output. We denote these data privacy requirements. In this setting, if the server returns nothing to the data analyst, no information will be lost to the client. However, the data held by their data broker will become completely useless. There are some prioritization methods applied by private work which uses heuristic approaches such as the identifying data, like medical records, or aggregated statistics, for example, the data released by the US sensors, or even in the forms of machine learning models for prediction, where you cannot find any individual records. However, existing work have demonstrated privacy vulnerabilities in all these approaches. Simple anonymization does not protect the sensitive information, as adversary can re-identify individuals based on external sources easily. Only releasing statistics does not work as well. For example, an internal team of the US Census have launched a tech that reconstructs records of address, age, gender, race, and ethnicity for about 46% of the US population using data publicly released under the 2010 decennial census. And then they can link part of this data to public datasets. Hence, it is not easy to guarantee privacy. Last, machine learning models also fail. Numerous studies have demonstrated that one can learn the membership of an individual in the training set that's used for training the model. And the fundamental issue here is summarized as follows. If we release too many statistics with high accuracy, we can reconstruct the database and hence fail the privacy. What is needed in the setting is a solution that allows studies and analysis about the population to take place while offering provable and promising privacy guarantees to individuals. As the query is sent by the data client, who is the attacker, and the query evaluation is run by the trusted data curator, we only need to worry about or provide the data curator a solution that offers strong probable privacy guarantee. The state-of-the-art privacy guarantee is differential privacy, which was proposed in 2006. Its goal is to protect the privacy of individuals in the database while releasing useful output of a valid computation to the untrusted clients. A differential privacy has been deployed in industry such as Google and Apple, and government agencies such as US Census. The reasons for differential privacy has been considered and deployed is because it has a formal privacy definition with clear assumptions. Algorithms that satisfy differential privacy always involve randomness, and they should always come with a proof. This randomness allows us to bound the information leakage, and we are going to see more formal definitions in its properties DP in Module 2. The trade-off for the privacy here is accuracy to the aggregated properties that a client wants to learn. Hence, we'll see most of the systems that support differential privacy has an optimization space between privacy and accuracy, unlike traditional database systems that orient at performance. However, we're going to see how differential privacy can also play a role in optimizing the performance of some systems in Module 3 as well. We have looked at the cases when we have a trusted data curator, right? However, in practice, data can be federated among many parties. For example, medical records are distributed among different medical centers. And how can a data analyst who is considered untrusted to analyze the union of this federated data? The first solution is to have an honest data broker to take the query from the clients and send the query to the corresponding data owners. And each data owner will run this subquery and return the query answer back to their data broker. And data broker will compile this query answer and send it back to the clients. But what could go wrong with this approach? First, for this to take place, we need a complex legal agreements between these data owners for data sharing. And to answer many of the queries, their private records sometimes have to be sent to their owner's broker instead of sending partial query results. However, this owner's broker may suffer a central point of failure for data breaches and saddles this broker with legal and ethical obligations to uphold data privacy. And there will also be side channel leakage with the communication between the data owner and the broker. In addition, each data owner can also observe network traces and query time to learn about the private inputs of the other parties. Or even answer cardinality, right, can be linked to each other. Lastly, the query output can also leak information about the input data to the client in the same fashion as the centralized setting. Hence, a different trust assumption should be considered here. We call this new set of trust assumptions private data federation. This assumes that none of the parties are trusted. In this private data federation setting, the untrusted client broker can be considered to have the same view. Similar to the client-server setting, we need to prevent the client and the data broker from inferring sensitive information about individuals from the released output. Hence, data privacy is needed again in this case. How about data owners? We assume the data owners here are semi-honest. They will honestly evaluate the query over the federated data, but they're also curious about other data owners' input and aim to infer them their computation, such as by observing encrypted data, intermediate results, or side channel information. To guard from this information leakage, we define a privacy requirement named computing with confidentiality. It is challenging to achieve this confidentiality, as we can see that no parties in this federated setting are fully trusted. Each has its own intent and capabilities. To overcome this challenge, we need to leverage special technologies to bring trustiness for computing with confidentiality. The first technology is local differential privacy. This local version of differential privacy can be applied when no central trusted data curator exists. Each data owner can perturb their input before sending it over to the data broker. This approach offers computation with confidentiality, as there are no computations involved between different data owners and data brokers. Even if the data broker is computationally unbounded, or if the remaining parties collude, the last data owner's data is still protected with bounded leakage. This, at the same time, ensures data privacy. However, the cost of this strong privacy guarantee is the loss of accuracy in the final query answer returned to the client. The second popular technology we want to talk about here is secure multi-party computation. This approach leverages cryptographic techniques to allow multiple parties to compute a function without revealing the private inputs. This technique has been used by, for example, the Boston Women's Workforce Council in 2017 to identify the wage gap between genders. Meanwhile, the companies who offer the data doesn't have to leak their raw wage information to the others. However, the computation cost of this approach can be very high, especially for complex queries. If we want to achieve this guarantee, additional performance costs needs to be paid. The third technology we want to talk about here is TE solution. This solution has been developed in the last few years. It places trust in hardwares, for example, TrustZone divided by ARM, SGX divided by Intel. Though these solutions provide better performance, they heavily rely on the security guarantee of the hardwares. If the security guarantee of this hardware fails, we then have to revisit the solutions. Note that all these three approaches offer security guarantees. However, those security guarantees are different, as they place trust assumptions at different parts of the computation. Their security guarantees can also be proven with these assumptions stated explicitly. In this tutorial, we'll dive into MPC and TEE in particular to understand their formal privacy definitions, assumptions, and their limitations. Now let's take a look at the last setting, where data owners' clients outsource their data to an untrusted cloud. All the issues that happen to the firmware settings can actually take place here as well, as the servers who store the data and process data are not trusted. They can be a point of failure during data breach. They can also view side channel information to infer about the data stored on the cloud. Hence, all the solutions applied to firmware settings such as TEE and MPC work here too. However, the key difference is that the client is trusted. It is the same party who owns the data and who queries the data. Hence, more information is allowed to be returned to the client. For instance, if the query is to retrieve all records generated by XI, to prevent the server from knowing that XI's records are retrieved, we can return all the records on database back to the client. This leads to a weaker privacy guarantee than computing with confidentiality, known as private information retrieval. This requirement says that the client can retrieve an item from a server without revealing which item is retrieved. Returning the entire database back to their client naively meets the requirements, but clearly it is not efficient. In fact, this is the only possible protocol that can give the client information theoretical privacy for that query in a single server setting. To address this problem, two approaches have been proposed. The first approach is to make the server computationally bounded. This enables many efficient solutions with a smaller communication cost. The second approach allows multiple non-correlating servers, each have a copy of the database. Again, these requirements have its formal and proper privacy definition. The payoff here is the efficiency and communication cost in retrieving items from the cloud to their clients. A symmetric version of private information retrieval happens in the firmware setting, known as private function evaluation. It is also considered a special case of multi-party computation that evaluates one party's private data using a private function owned by another party. We won't be able to go through each technique one by one, but this table summarizes the key techniques for semi-honest model. In addition, we'd like to quickly discuss the techniques for the case when parties behave maliciously. In this model, there are additional integrity constraints. The malicious parties can act maliciously and deviate from given protocols, such as apply unauthorized updates to the data or apply incorrect query evaluation. The security and privacy solution aims to detect and defend against such behaviors. General approaches include using authenticated data structure, ADS, such as Merkle tree and blockchains. Special MPC technologies such as zero-knowledge proof and TEE technologies can also be used here to defend such a malicious party. But the performance overheads are significantly higher here than semi-honest attack model. Existing efficient solutions could only provide partial integrity for part of the data or part of the query, and sometimes against just a special type of malicious behavior. Composing of the existing methods for an end-to-end integrity guarantee still remain as an open question. Now we come to the end of this module. In this module, we overview the desired privacy and security requirements in three reference architectures. These privacy and security requirements greatly depend on assumptions made in different settings, and the corresponding approaches also vary. Note that each of the security and privacy guarantee has to pay a cost. Hence, in the following modules, we'll illustrate both the formal definitions and the trade-off between privacy and other aspects of the systems. Thanks very much for attending the first module. We're happy to take some questions.